Okay, everyone, good afternoon again. So, in this session now, we're going to continue doing examples with featuring the Heaviside step function. So, when I last saw you, we just completed example 1 there, example 212 part 1. The main piece of work we're going to do shortly is example 213, solving that differential equation featuring the Heaviside step function. But just before we do, let's just have a short look at this other example, 2.12 part 2. So here we are looking at this function u of s. So this is the transform we're presented with. E to the minus 3s plus e to the minus 3s all over s squared plus 1. And so the task here is to find the inverse Laplace transform. Little u of t is the inverse transform of capital U of s. Okay. So, by linearity, you're always looking to use the linearity property of the transform and its inverse where appropriate. So here we're taking the inverse transform of capital U of s. Capital U of s is itself a linear combination, sum of two functions. So its inverse transform will be the sum of the individual inverse transforms. And on the work we've done earlier today, seeing an exponential on its own like this, e to the something times s, that's come from transforming a certain Dirac delta function. So that the inverse transform of that will be delta of t minus 3. So that's using theorem 2.2.6. This one here, this part here, so this we reckon, so what's going on here? Here we've got a product of an exponential, e to the minus 3s, multiplied by 1 over s squared plus 1. Now if you look to the table of Laplace transforms, you don't find anything exactly of that form in the table, but we do find a 1 over s squared plus 1. 1 over s squared plus 1 would be located here with omega equals 1, so its inverse transform will be just sine of t. I know the sine of t. But it isn't just that on its own, it's this exponential, e to the minus 3s multiplied by. So to handle that, we need to be comparing it with theorem 2 point, whatever it's called, 2 point something, but this is it summarized here. So this was the last, so this was the second result about the transform of the Heaviside that we proved today. That the transform of something times a Heaviside gives you this exponential times an f bar of s. So that's the exponential e to the minus as times f bar of s. So that's what we're looking at here. You've got this exponential e to the minus 3s, so that a is 3, and that's multiplied by 1 over s squared plus 1. 1 over s squared plus 1 is the transform of the function sine of t. So putting all that together, the inverse transform here is going to be the product of sine times h of t minus 3, but the sine function is itself evaluated at that same shifted argument. Okay, so that'll be sine of t minus 3 times h of t minus 3. So what I'm using there is using theorems 2.6 for the Dirac delta function and 2.5 to handle this term. So just a couple of quick examples, just going forwards and backwards, taking the transform and inverse transform of a couple of examples featuring the Heaviside step function. So I think next we'll be looking at example 213. Okay, so a genuine problem, an ordinary differential equation featuring the Heaviside step function. Before we move on to that, any clarification or queries needed before we leave? Okay. Okay. So let's look at this example 2.13. And it's running out. Okay, so here in 2.13, we see an ODE featuring a Heaviside step function, and we're supplied with initial values as well. It's a second order ODE, meaning you've got second derivatives. I'll just write it using the more compact notation here. So you got y double dash minus 4 times y dash plus 3y equals 6 times the Heaviside of t minus 5. And this is subject to initial conditions, these nice 0 initial conditions that the initial value of both y and its derivative is 0. That will simplify the transformed equation somewhat for us. But it's a typical set of initial values, because if y of t is indicating the position of something, if this is some kind of dynamical ODE measuring the movement of something in time, then these two initial conditions would correspond to the thing beginning at rest at some fixed point, y equals 0 at time 0. So it's not an uncommon set of initial values. So let's go ahead and solve this. Now the presence of the Heaviside function won't affect us too much. We'll just follow the same procedure as we did before. Okay? Because we brought in this new function, this Heaviside step function. We know what its transform is. We know how to take transforms of it. We know how to do inverse transforms involving it. So it should just slot right in to the established way we had for treating these equations anyway. Okay. So the first step is to transform both sides of the ODE. Transform both sides of the ODE. Just put in brackets, again, the properties we're making use of, we're using linearity, transform of derivatives property, and new property about transform of Heaviside. Okay, we're using all of these properties as we go. So the transform of the second derivative, y double bar, and we'll also agree to we'll write y bar equals the Laplace transform of y t. So the transform of y double dash, which is the second derivative of y, that's going to be s squared times y bar minus s times y dash 0, the initial value of the first derivative, minus y 0. So all of that is the transform of the second derivative term, y double dash. Then you'll have minus 4 times, because I'm using linearity here, so the transform of 4 times the derivative is just minus 4 times whatever the transform of the derivative is. And that's s y bar minus y 0, the initial value of y. Continuing with linearity, then you got 3 times y, so that will transform to 3 times y bar. And linearity on the right-hand side, 6 times Heaviside, so that will transform to 6 times whatever the transform of the Heaviside is. And this is Heaviside h(t minus a, where a is 5. So it has to transform e to the minus 5s over s. For some reason, when I cooked up these examples, I had craziness always paired 5s with s's. So I apologize for the use 7s. Easily distinguishable. But there we go. So make your 5s and s's distinct. Okay, so that's the transform of the whole ODE, fine. It's still featuring these constant initial values of y and its first derivative. We know that those are zeros, so we should apply those values now, because that will simplify the presentation. So you've got s squared y bar, 0, 0, minus 4s y bar, 0, plus 3 y bar there, and still 6 e to the minus 5s over s there on the right hand side. Okay, using initial values. Okay, that's good. That simplified the equation. And what we're aiming to do now is to solve it for y bar, meaning to make y bar the subject of it, so we can see the formula, if you like, for the function y bar of s. So that's not hard to do, because you got stuff involving s on the right hand side, stuff linear, sum of terms. Each term has a y bar in it, and the other terms are s's, so you can factorize out here. So you've got this polynomial s squared minus 4s plus 3 times y bar is this here. And that implies that y bar is 6 times e to the minus 5s over s, divided by this polynomial, and we may as well factorize it as we go. This is s minus 1 by s minus 3. Isn't it? S squared minus 4s plus 3. So this is our solution to the transform problem. We now have to take the inverse transform of it to recover the original solution y d. Okay, take the inverse transform of it, fine. So, okay, it's a bit complicated. You won't find anything of that form on the table. But again, the format that's taking there, bring the table up, is again it's going to be an instance of this result here. Okay, because what we were looking at there on the page a minute ago, we'll look at it again now, is e is some exponential e to the minus as multiplied by an f bar, multiplied by something that we recognize as a Laplace transform. Okay, because it is multiplied by 1 over, okay, 6 there as well, 6 over s times s minus 1 times s minus 3. Now that function on its own in terms of s, 6 over s times s minus 1 times s minus 3, that itself isn't on the table. But we know that if we took a partial fraction expansion of that function, it would be a combination of basically this type here. 1 over s plus something, and that's the transform of an exponential. And a 1 over s bit, which is the transform of a constant. Okay? So that exponential bit, we should just kind of leave that here. What will I do with 6? Yeah, so let's take out 6 as well. So this is 6 times e to the minus 5s times 1 over s minus 1, s minus 3. Okay, all I've done there is just shift the 6 and the exponential bit out to the left, just leaving this function on the right. Okay. But this function here, this whole thing here, is playing the role of that f bar of s. This is the f bar of s in the result on the table, which is theorem 2.6, I think. Okay. So we have to basically figure out what the f of t is. Okay. Because the inverse transform of this, y of t, which is the inverse transform of y bar, using that rule, this is going to be 6 times Heaviside h of t minus a, so this is t minus 5, times f of t minus 5. That's using the result from the table. Which is theorem 2.6, in other words. So we just have to identify what that function f is. Sorry, not theorem 2.5, sorry. 2.6. 2.5. Okay, and I can identify what the f of t is by going for a partial fraction expansion of that thing, 1 over s times s minus 1 times s minus 3. Or 1 over s times s minus 1, s minus 3. Should I go through the details of this, or should I put down the answers? I know the coefficients already. I think we've done a few of them lately, so yeah. I'd rather there's more instructive stuff if I can get on to the next example as well. So I prepared earlier the correct partial fraction expansion coefficients of this. So they are a third, a sixth, and a minus a half. Okay, so the details skipped. Details skipped with that derivation. It's just the normal, regular partial fraction expansion. I should have left the 6 in, because I know we've simplified those somewhere. And this thing, so this is our f bar of s, and so this implies that f of t, well, I just take the inverse transform of all of this. So it's going to be 1/3 plus 1/6. So go back to the table to take this inverse transform, and yeah, the sign changes. So this is e to the 3t, and this is minus 1/2 e to the t. Okay, so that's taking inverse transforms from the table. So we've successfully identified the function f of t there. So I can now go back and get my solution to the original ODE. So the solution y of t to the original ODE is y of t is the Heaviside h of t minus 5, and there's a 6 there, but I'll use the 6 to clear some of these, clear those coefficients. So when you multiply through that 6, you're going to get coefficient 2 plus exponential. Now, exponential of what? It's exponential of f evaluated at t minus 5, not to t. So it's e to the 3t minus 15. And then minus 1/2, but I'm multiplying by this 6, so that would be minus 3 times the exponential, but not exponential of t, it's f evaluated at t minus 5, so it's exponential of t minus 5. Okay, so that's what the solution to the original ODE looks like. It's essentially this function here, 2 plus this exponential minus 3 times that exponential, but that function only, it's only this function after a certain point, after t equals 5. Previous to t equals 5, it's just 0. Okay. So the presence of the kind of switched signal in the original ODE is kind of mirrored in the presence that the solution to itself is a kind of signal that gets switched on at t equals 5. Previous to that, it's just 0. So there's not much happening before t equals 5. Okay, any questions about that example? So we skipped over the minor details of getting the partial fraction expansion coefficients. But that's kind of pretty standard technique by now. Okay, so in the remaining time, there's a nice exam question from not last year, but the year before. I thought we might take a look at 2015, I believe. Yeah. So, okay, so this is from 2015. So this is the whole question, 20 marks here, which is basically the question solved out ODE in part C. And parts A and B are just dealing with this function f of t, 27 f of t, which is on the right-hand side of the ODE. That function f of t is the one introduced in part A. So it kind of steps you through. Parts A and B are getting you to use Heavisides to get the Laplace transform of that function f of t, and then with that knowledge then to solve the ODE. Okay. So this is a good, will be a good workout of all the ideas that we've seen introduced today. Okay. So please do stop me at any time with any queries you might have, any clarifications. Sorry?
You just show the last bit, please.
Oh, sorry.
Sorry about that.
Took it on too much. So do stop me at any point. Okay. Yeah. Any other queries? So this is 2015 question 4. So let's look at part A. Okay, so we're presented with this function 0 outside the interval, 0 to 4, and inside the interval is as shown. So it's 0 everywhere except between 0 and 4. And between 0 and 4, it's made up of these two straight line bits. Two straight line bits. So the first question there. First question there asks us to explain how this function f is represented as a combination of Heaviside step functions, given the correct answer to work towards. Okay, that's not immediately obvious. It doesn't just kind of leap off the page at you. So you do have to approach it bit by bit. So let's look. Let's first of all try and get a description of f of t. Get a case-wise description of f of t. Well, you see it's got 3 different types of behavior. It's got a behavior between 0 and 2. It's got a behavior from 2 to 4. And then it's got a behavior otherwise. T is what, less than 0, or t greater than 4, greater than or equal to whatever. And that's the easiest one, because it's said so in the function. It's 0 everywhere outside that interval. But what's it doing in these two cases? So in these two cases, we should have straight line formulas. So the first bit is easy. It's going from the origin up to the point 2, 2. So that's clearly the line t. Without too much difficulty. Then coming down on the way back, well, it's a line with negative slope because it's decreasing, and it decreases by 2, from 2 down to 0 in the space of a change in 2 in the x-coordinate. So it's got slope -1, so it's minus t. Then you just have to think what the intercept of it is. Well, it's 0 when t is equal to 4. So the only way to get it equal to 0 when t equals 4 is to have the constant be plus 4. Okay? And that we recognize as the expression for a straight line. Y equals mt plus c. Okay, so that's good. We've got an expression for the function f in those terms. And then we use the idea of, say, this thing we discussed this morning, h of t minus a minus h of t minus b. This is this thing which is 1 between a and b and 0 otherwise. We can use that idea to write f of t as being, so it's this expression t times h of t minus h of t minus 2. So this bit is a chunk that's 0 everywhere except between 0 and 2, and between 0 and 2 is equal to t. So this bit will generate this upward ramp on the left. And then you can add on to it minus t plus 4 times h of t minus 2 minus h of t minus 4. Because this part considered on its own, is 0 everywhere except between 2 and 4, where it takes the value minus t plus 4, which will generate that second downward ramp from 2 to 4. And we don't need to add anything else to it, because the only other behavior we need to generate 0 at all these other values of t, but these two things are defined to be 0 at all other values of t. So that's a full stop there. F of t is equal to that. And now we might want to reorganize this slightly, because we've got h of t minus 2's in both parts, so we maybe want to collect together all of those. So it's t times h of t minus 2. Now what have we got here? We've got minus t times h of t minus 2 and minus t plus 4 times h of t minus 2. So it's plus, you got minus 2t plus 4 h of t minus 2. And lastly, you got minus t plus 4 h of t minus 4. So we could write that as t minus 4 times h of t minus 4. So this minus sign multiplies into that bracket in terms of plus t minus 4. And a convenient way to change this yet again, which I think is to get it to how it is in the answer, is to take out the minus 2. That's t minus 2, h of t minus 2, plus t minus 4, h of t minus 4. So this is as required. That's the expression that's given to us there. As required. Anybody know what that's from? That quote? As required. Winnie the Pooh. It's how Winnie the Pooh pronounces required. I'm reading that to my kids. I recommend Winnie the Pooh. There's a lot of cleverness in Winnie the Pooh. And the conversations between the animals. There's a lot to be found. Is it him who means that, or is it Owl? It might be Owl. Maybe it's Owl. He's supposed to be wise, but really it's question. I think that's how he pronounces required. Okay. So that's part A. That's part A. Part B is to take the Laplace transform of that. And clearly state any results about Laplace transforms that you make use of. Well, okay. To deal with that, we need linearity transform, and you may as well clearly state it. Now I won't write F because F is already in use here, so I'll call it a G. The Laplace transform of G of t minus A times H of t minus A, that is exponential e to the minus AS times G bar of X, the Laplace transform. And actually we see it's the same function G involved in all three terms of F. Namely, the function defined as G of t equals t. So that function, the identity function if you like, G of t equals t, sorry, that what I wrote there, h of t minus 2 is wrong, that's just h of t, so it's just a transcription error, it's t, h of t, t, h of t. So that first bit is G of t, h of t, then you got minus 2 times G of t minus 2, h of t minus 2, and then at the end you've got G of t minus 4, h of t minus 4. Using this particular G, G of t equals t. So it's more or less that same function involved, except the one in the middle has an extra coefficient of 2 in front of it, but we can deal with that by linearity. Sometimes people find this a slightly confusing point because, yeah, it's pretty clear. You got t here, t minus 2 there, t minus 4 there. Why am I writing a g in front of it? Well, but it's just to emphasize that in order to take the Laplace transform of expressions like this, so the function of t multiplied by h, they have to be set up and presented in such a way that the function in front of the h is evaluated as a function of the same argument. In this middle case, t minus 2, and in this case here, t minus 4. And in that previous case, just t on its own, t on its own. And it is indeed presented like that, and it's the same function involved. G of t minus 4 there, meaning just t minus 4, G of t minus 2, t minus 2, G of t minus 2. So that would imply then that the Laplace transform of F is so G of t is equal to t, so the transform of the g part is just 1 over s squared, and then that gets multiplied by e to the minus as. The a here is 0, so it's e to the minus 0 times s. It's minus 2 times 1 over s squared, e to the minus 2s. And there it's plus 1 over s squared, e to the minus 4s. But that would simplify because e to the minus 0 is just 1. So that would be 1 over s squared minus 2 over s squared, e to the minus 2s, plus 1 over s squared, e to the minus 4s. Okay, and that's the conclusion to part B. Obtain the Laplace transform of that function. And we'll need that for part C. So for part C, we're going to solve this ODE here. d2y dt squared plus 9y plus 27 times f of t. So that's that same f of t. Part A, we've already got its Laplace transform there. Part B. So we'll be able to make use of that now. So in C, we want to solve y double dash plus 9y equals 27 f t. So you take the Laplace transform of both sides, you'll have s squared times y bar minus s, the initial value of y, plus derivative of y minus the initial value of y, plus 9 times y bar equals 27 times all of this thing up here, which we just worked out, the Laplace transform of f of t. I could have brought the 1 over s squared out in front, actually. I might do that next one. So, the initial conditions are both 0, as supplied in the question, so that simplifies it somewhat. And we'll have s squared plus 9 times y bar. Yeah, I'll just bring out the s squared here. So it's 1 minus 2 e to the minus 2s plus e to the minus 4s. Just taking out the 1 over s squared out to the front. So then you can solve the transform problem. Y bar is 27 over s squared times s squared plus 9 times 1 minus 2 e to the minus 2s plus e to the minus 4s. So we've solved the transform problem. So in principle, you just have to take inverse transforms. Now we need the inverse transform of this. Yt, the inverse transform of y bar. Now, what kind of structure has this got? Okay, it's a linear. Okay, I've written it as a product of things, but if you multiply out this bracket, it would be a linear combination of this thing here, 27 over s squared plus 9, and multiplied, well, either on its own, multiplied by 1, or multiplied by a certain exponential. So to take the inverse transform of that, we have to take the inverse transform of this bit here, 27 over s squared plus 9, or take the inverse transform of that multiplied by an exponential. So again, we'll be going back to using, let's just slide it down behind there, that property there that's appeared just here. This is the key property. We're going to have to use this in reverse now. So if we're looking at, what we're looking at here is 3 examples, well, excepting the 1 times that, but 2 examples of an exponential times a transform of something. Now to understand what the inverse transform of this is, we'll need the partial fraction expansion of this. Now, okay, in general, this might get a bit hairy, but it's 1 over s squared plus 9, and we need to get it to give a constant. Well, if there's no s squareds left when you bring it together, that means these 2 coefficients must be plus and minus of each other, so that when you multiply it together again, you get no s squareds. And if you want to get a 27, it means you're going to have to have a 3 over here. 3 times 9 will give you that 27. So then it has to be a minus 3 there. You got those two multiplied by this. So if we call that our h of s, say, we'll need the function h of t, which is the inverse transform of h of s. Well, 3 over s squared, that's the transform of 3t. And minus 3 over s squared plus 9, that's exactly the transform of sine of 3t. Okay, that's from the tables. So, using, again, that result in the tables, but it's theorem 2.6, wasn't it? 2.5, excuse me. Using theorem 2.5, y of t is the inverse transform of y bar. When you multiply y bar out, you have 1 times that. Okay, so you're going to have h of t. Well, I've already taken the inverse transform of this here. And then you've got this minus 2, so using linearity, and then e to the minus 2s. So it's going to be the Heaviside of h of t minus 2. The minus 2 because of that minus 2 up here. And that's multiplied by the little h, this other function, little h, of t minus 2. Okay, because I'm taking the inverse transform of this exponential multiplied by this function. So using that result from theorem 2.5, this is the inverse transform. And finally, take an inverse transform of the e to the minus 4s times that. It's plus h of t minus 4, again times h of little h this time of t minus 4. So if we really wanted to see it in terms of just standard functions of little t, it would be h of t, so it would be 3t minus sine of 3t. This minus 2 bit, and this little h of t minus 2 would be 3t minus 6 minus the sine of 3t minus 6, because it's evaluating little h of t minus 2. So that t there gets replaced by t minus 2 for this part. Close that bracket. And that's all multiplied by Heaviside h of t minus 2. And then lastly, it's little h of t minus 4, so it's 3t minus 12. 3t minus 12 minus the sine of 3t minus 12. And that's all multiplied by Heaviside h of t minus 4. And yeah, I wouldn't keep at it much more than that. That's about as straightforward maybe as we could get it down as. So that's what the solution to the ODE is going to look like. It's got this part 3t minus sine of 3 of t, which is always there. And then these other parts only get switched on. Well, the second part gets switched on as t goes past 2. Then this term switches on, and then you finally get this third bit added to the solution as t passes through 4. So the presence of this, it's still there, yeah, the presence of that ramp type function in the ODE as this kind of driving force term f of t here in the right hand side of the equation. The effect of that is seen in the solution to these various parts that get switched on at various excuse me, various times. Okay, that's good. That's good timing. There's two little sections, 2.6 and 2.7. You can see there in the notes. We'll deal with them quite quickly, saying half a lecture or so. So we've probably just got one more lecture in this unit. We'll do some more examples, and with our tutorials this week, we can do some work on the tutorial problems here. Okay? So thanks for your attention. I'll see some of you now in the tutorial. You've got your tutorial now.
Cheers. Thank you very much.